Hey everyone, welcome back to the channel. Before we dive deep into any single chapter of Additive Manufacturing Essentials, we need to talk vocabulary. Here is why this matters. Additive manufacturing sits at the intersection of engineering, materials, science, software, business, and quality systems. Every one of those fields brings its own language to the table. If you walk into a conversation about AM without knowing the terms, you will miss the meaning even when you understand the words. Think of it like trying to follow a recipe written in a language you only half speak. You might recognize flour and eggs, but if you miss the word for sift, the cake falls flat. So today we are building your foundation. 15 to 20 essential terms, grouped by theme, each one grounded in a real-world example so the definition actually sticks. Let us get into it. Theme 1. The basics of how AM works. Let us start with the most fundamental concept of all. Additive manufacturing, or AM, is the process of building a three-dimensional object by adding material layer by layer from a digital model, rather than cutting or shaping material away. Think about how a traditional machinist takes a block of aluminum and mills away everything that is not the part. AM flips that completely. A medical device company, for example, uses AM to build custom titanium implants that match a specific patient's bone geometry, something impossible to achieve economically with traditional machining. Closely related is the term layer-by-layer fabrication. This is the actual mechanism behind AM. Each cross-section of the digital model is deposited or fused one at a time, stacking until the full object is complete. A good way to picture this is a CT scan in reverse. Instead of slicing an object to see inside it, you are stacking slices to build it from nothing. Next, feedstock. This is the raw material fed into an AM system to create a part. Feedstock can be a powder, a wire, a filament, a resin, or even a sheet of material depending on the technology. An aerospace supplier might use titanium powder as feedstock for a rocket bracket, while a consumer product company uses a plastic filament to prototype a new phone case. Theme 2. Core Technologies. Now let us move into the major AM process families. Powder bed fusion, or PBF, is a category of AM where a heat source, usually a laser or electron beam, selectively melts or sinters regions of a powder bed to form each layer. The powder acts as both the build material and the support structure. GE Aviation uses laser powder bed fusion to manufacture fuel nozzle tips for the LEAP jet engine, reducing a 20-part assembly down to a single printed component. Directed energy deposition, or DED, involves focusing thermal energy to fuse material as it is being deposited, often through a nozzle. It is frequently used for repair work. The U.S. Navy uses DED to restore worn ship propeller shafts, adding material back to a damaged surface and returning the part to service instead of replacing it entirely. Binder jetting is a process where a liquid binding agent is selectively deposited onto a powder bed to join particles. No heat source melts the powder during printing. The part is later cured or sintered. Voxeljet uses binder jetting to produce large sand casting molds for automotive manufacturers, molds that would take weeks to machine traditionally. VAT photopolymerization covers processes like stereolithography and digital light processing, where liquid resin is cured by light. Dental labs use this technology extensively to print highly accurate crowns, surgical guides, and orthodontic aligners directly from patient scans. Theme 3. Materials. Let us talk materials, because what you print with determines almost everything about what you can do with a part. Polymer in the AM context refers to plastic-based materials, including thermoplastics and photopolymers, that are among the most widely used feedstocks. A consumer goods company printing ergonomic tool handles for rapid prototyping is almost certainly working with a polymer like ABS or nylon. Metal AM materials include alloys like stainless steel, Inconel, titanium, and aluminum. These are used when a part must carry structural loads or survive extreme environments. SpaceX prints rocket engine components from Inconel using AM because the material holds up under intense heat and pressure. Anisotropy is a critical property to understand. It means that a material's mechanical properties differ depending on the direction you measure them. Because AM builds layer by layer, parts can be stronger in one orientation than another. An engineer designing a load-bearing bracket for a satellite must account for anisotropy to make sure the part will not fail along a layer boundary during launch. Theme 4. Design for AM. Good design is what separates a part that works from a part that could not be made any other way. Design for additive manufacturing, or DFAM, is the practice of intentionally designing parts to take full advantage of AM's capabilities, rather than simply replicating a design made for conventional manufacturing. Airbus redesigned a cabin bracket using DFAM principles, producing a lattice structure that is 45% lighter than the original machined version while meeting the same load requirements. Topology optimization is a computational method that mathematically removes material from a design wherever it is not needed to carry load, resulting in organic, lightweight shapes that would be impossible to make without AM. NASA uses topology optimization combined with AM to produce lightweight structural parts for spacecraft where every gram counts. Support structures are temporary scaffolding printed alongside a part to support overhanging features during the build. They must be removed after printing, which costs time and money. A well-executed DFAM strategy minimizes support structures by adjusting part orientation or redesigning overhangs, reducing post-processing significantly. Theme 5. Quality, Qualification, and Certification. This is where AM moves from the lab into regulated industries. Qualification is the process of proving that an AM system, material, and process will consistently produce parts that meet specified requirements. A medical device manufacturer must qualify their entire AM workflow before a printed implant can be used in a patient. This includes the machine, the powder lot, the process parameters, and the operator procedures. Certification is the formal recognition by a regulatory authority that a product, process, or system meets defined standards. The FAA certifying an AM-produced aircraft component for flight is an example of certification. Qualification supports certification. You qualify the process to earn certification of the product. Process parameters are the specific settings: laser power, scan speed, layer thickness, build temperature, that control how a part is built. Changing even one parameter can alter microstructure and mechanical properties. This is why AM facilities lock parameters down as tightly as a pharmaceutical company controls a drug formulation. Theme 6. Digital and Business Context. Finally, AM does not exist in a vacuum. It lives inside a digital ecosystem and a business strategy. The digital thread is the connected flow of data that links every stage of a product's lifecycle, from initial design through simulation, manufacturing, quality inspection, and field use. In AM, the digital thread ensures that the exact parameters used to print a certified aerospace part can be traced, audited, and reproduced years later. Lockheed Martin uses digital thread frameworks to maintain traceability on AM parts used in classified satellites. Build file is the specific digital instruction set sent to an AM machine, derived from the original CAD model after slicing, support generation, and parameter assignment. Think of it as the recipe the machine follows exactly. Any change to the build file must be controlled and documented, especially in regulated industries. Total cost of ownership is the full economic picture of producing a part with AM, including machine cost, material cost, labor, post-processing, quality inspection, and qualification expenses. A company might find that AM costs more per part than injection molding, but saves money overall by eliminating tooling, reducing inventory, and enabling on-demand production. Understanding total cost of ownership is what separates a smart AM business decision from an expensive mistake. All right, let us land the plane. You now have a working vocabulary that spans the full arc of additive manufacturing, from how material is deposited layer by layer through the major process families into materials behavior, smart design strategy, quality and regulatory requirements, and the digital and business systems that hold it all together. These terms are not just definitions to memorize. They are the conceptual handles you will grab every time a chapter gets technical, or a real-world application gets complex. If you want to go deeper on any of these concepts, every chapter in this playlist has its own dedicated video that unpacks the details, explains the engineering, and walks through more examples. Start with Chapter 1 if you are brand new, or jump to the chapter that matches what you are working on right now. Hit subscribe so you do not miss any chapter drops, And drop a comment below telling us which term surprised you most or which one you want explained in even more detail. We read every one. See you in the next video.